the video due to the problem with the sound.
Sure.
Thank you.
And please, do you agree to be recorded? Caterina, puoi condividere?
Sì.
Drone detection with YOLOv5. Introduction. With the massive proliferation and popularity of drones, the technology has become affordable and interesting for the masses. Thus, the technology that was in the past years affordable only for the military is now used by terrorists, for example for bomb attacks. To eliminate such combat drones, they must be detected and localized as precise as possible in very fast manner. The paper proposes a drone detection method based on neural network architecture. The method detects drones in videos in a visible RGB and infrared spectrum. Method. With regard to the inference time required in real deployment, the paper utilizes YOLO architecture in version 5 for drone detection. YOLO architecture provides state-of-the-art performance while maintaining fast inference. The model is a one-stage regression-based detector, meaning that objects are predicted by bounding boxes that take the form of quadrangles. As nonlinear functions, leaky rectifier linear unit and sigmoid linear unit are used. The paper inspects the performance of the YOLOv5 model in 4 sizes: small, medium, large, and extra large. And the UAV dataset for unmanned aerial vehicle tracking was used for training and testing due to the closest similarity to the real deployment from all publicly available datasets. Dataset consists of 100 high-quality video sequences in a visible and infrared spectrum spanning multiple occurrences of multi-scale UAVs, tiny, middle, and big. The training was conducted in 20 epochs for each variant. Stochastic gradient descent was used as the optimizer, and data augmentation such as random cropping was used in the training process. It is customary to use out-of-shelf GPU servers for evaluation of object detection models. However, we cannot expect the use of high-end or professional GPUs in the real deployment due to their immense power consumption. Thus, the experiments were conducted not only on a server, but also on an embedded system. The server contained AMD EPYC 7351P processor and NVIDIA 20 Ti graphic card. Jetson AGX Xavier was used as the embedded system. Results. In Table 1, you can see the performance of the YOLOv5 models on the infrared videos, and in Table 2, performance on the RGB videos. From the results, we can clearly see that even the smallest size of the YOLOv5 provides enough capacity to detect drones in both infrared and RGB videos. What is worth of the note is the column AP 50 to 95, which denotes average precision for thresholds from 50 up to 95% with a 5% step. This column shows that the YOLOv5 provides detection in RGB videos with higher confidence. In Table 3, we can see the inference time results for GPU, CPU, and embedded system. The results show that the YOLOv5 model provides sufficient speed for both the GPU and embedded system. Assuming limited power consumption for the deployment, the embedded system provides the best trade-off between speed and consumption. The results also show that CPU deployment is not suitable for such a task. In Figure 1, you can see the result of the YOLO V5 in a small size on the RGB video frame from the UAV dataset. The blue rectangle denotes the area where the drone is detected, and the number denotes confidence of the prediction. In this case, the model detected the drone with 80% confidence. In Figure 2, you can see the results of the YOLO V5 in a small size on the infrared video frame from the anti-UAV dataset. As in the first figure, blue rectangle denotes detection and the number denotes confidence of the prediction. Conclusion. In the paper, the YOLO V5 model of different sizes was utilized in order to detect drones in visible and infrared videos. The models were trained and tested on the anti-UAV dataset, showing the capability for drone detection for combat and real-world environments, while maintaining fast inference. The paper has also provided a comparison between out-of-the-shelf GPU server and embedded system, showing the embedded system as a suitable system for the power consumption restricted environment.
Thank you. Thank you for the interesting presentation. And are there any questions from the attendees? Any questions? I forgot to mention that the author is an ICT specialist and artificial intelligence engineer and he works as a computer vision researcher and engineering at the Czech Technical University in Prague. So no any questions. I have one question for you. I mean, the data set, do you think they could cover even some other kind of structures like fixed wing vehicles or something like that? Or do you expect to have to upgrade the system to guarantee the detection or vehicles?
Yeah, so if I understand well, so the question is whether the data set is well enough.
Yeah.
Right? Yeah. And not even close to real world deployment, I believe. It is the closest, or the similarity, it's the closest data set for real world deployment, but the data set consists of only 100 videos and usually only one object, only one drone is on the frame. So it's a problem for false positives and false negatives examples. So it's also the reason why the detection is so good. But this data set is the closest to real deployment. But another problem which the paper points out is that there is no publicly available data set for such a task. So there is even no benchmark. So we can't compare different methods between and yeah, not even close to real world deployment. Yeah.
Thank you. Any other questions? Yes, Thomas?
Did you mean me? I'm not Thomas.
Christoph, sorry.
No problem. I have an additional question. You mentioned that you have used different augmentation methods for the training of your model. Which augmentation methods did you use specifically?
I was, from top of my head, there was a random cropping and rotation, and changing of aspect ratios.
Okay, so you have used your 100 videos of the dataset and applied those to augmentation methods. Do you know how many result images you were able to generate like this? So how huge was your training dataset in the?
Yeah, I understand that. Yeah, I wasn't I wasn't preparing from by the augmentation another data set. It was run in the real time, so there was random cropping. So every time the frame was passed to the network, it was randomly augmented. So we can say that for each pass, each frame was different. Right, so I was not creating a new data set. It was in runtime.
Oh, okay, thank you.
You're mostly welcome.
Thank you. Any other questions? No? Okay, thank you. Thank you so much. Thank you so much for your presentation. Nice presentation.
Thank you. Thank you. Have a nice day.
Thank you. Bye.
Bye.
Okay, and then we can move on the next one, the second paper in these sessions, Modeling Team Cohesion During Military Conscriptions, a Multidimensional Model for Task Cohesion. Are the authors here? Any one of the authors? There is any speaker for this paper? Is there any speaker for this paper? No. So Katerina, please, what can we do? Just play the video, okay?
Okay, I share the video.
Okay.
I would like to present our research and our paper that is designed for the modeling team cohesion during military conscription. And for this reason, we used multidimensional model. Talking about the concept of the research, we can say that task cohesion is one of the most powerful drivers that determine the team determination to achieve the set of goals together. And for sure, the task cohesion is highly important for the compulsory military service because it defines the effectiveness of small military unit and in general the efficiency of the compulsory military service. Talking about the teams in general, is really very important to say that teams are developed and also dominated by the nonlinear feedback networks where the team cohesion is developed. And talking about that, for sure, these relationships can only be understood using nonlinear models that are able to capture the complex dynamic of these interactional processes. And mathematically, artificial neural networks modeling is used for this purpose. Talking about the artificial neural networks, it has an advantage because it could be applied and it could find the pathways underlying a complex set of data and to discover hidden associations between different factors. And therefore, an artificial neural network can be investigated can investigate the complex associations between the levels of dependent and independent variables. Taking all this together, we identified the research gap that talking about, especially from the social sciences, the methodologies do not allow to predict the task cohesion in the nonlinear feedback groups, and therefore artificial neural networks could be applied. Therefore, we raise our research question, and our research question is how to analyze, model, and predict task cohesion in conscript teams, considering that teams are dominated by nonlinear feedback networks. Materials and methods we used, the analysis of the study was performed by employing the artificial neural networks modeling. And for this purpose, neural networks model such as multi-layer perceptron and the radial basis function were built to predict the team cohesion in conscript squads. And the analytical measures of the design models were assessed by comparing the results data, and for validation, we used two statistical values, the determination coefficient and the mean square error measures. There were also constructed neural networks model with one hidden layer, and reducing the error functions helps us to optimize the number of units in the hidden layers. For modeling analysis, the study database was divided into three portions: training, testing, and holdout. And the IBM SPSS software was used for the modeling. Talking about the sample and data collection, 11 squads, military squads of the conscripts, with totally of 111 conscripts in the first months of their service were surveyed. And it took place in one battalion of Lithuanian Armed Forces during the COVID pandemic. And by the way, this circumstances created really a perfect environment for this research, as the impact from the external environment was minimized because of the social distancing from the environment. Altogether, we had some measures, and before that, after the task cohesion in conscript squads was measured in the context of group cohesion factors, and also we involved not only that, but also leadership and individual factors of each conscript in the squad. And totally components were developed into three groups: group cohesion, leadership, and individual factors. And all of them are listed in the slide. After the numerous neural network modeling, different multi-layer perceptrons and the radial basis function constructs were created and verified. And this comprehensive modeling was completed to create an acceptable structure with appropriate numbers of hidden layers and neurons. The results of our neural network modeling are presented here. They identified now how the task cohesion could be forecasted by 8 independent variables. As a result, the green line represents the best multi-layer perceptron. It is in the MOD2 model. For team task cohesion, it was constructed with one hidden layer and 20 neurons and one output. And the red line represents how the radial basis function, MOD8, predicts the changes in team task cohesion in 11 squads according to the measurement. It was designed with the training 40%, testing 40%, and holdout 20% of the datasets partition. The softmax function was used for hidden layers activation and for the outcome layer. So totally identified, we used 8 input neurons, 22 neurons in the hidden layers, and 1 output. The robustness of the designed neural networks you can see in the table. So 2 tests of statistical differences between the team cohesion measurement and 2 different constructs of neural network models were conducted. According to these 2 figures, they illustrate that the results of the normalized importance of variables for 2 neural networks models using 2 different types of them showed statistically significant high validation results by determination coefficient. And despite the fact that these 2 models high validated, the importance of variables in task cohesion predictions are quite different. And in the first one, we have that the task cohesion is on the top, and in the second one, the task cohesion mainly is in the second position. What is really most important is that in both of these models, independent variables that we measured around the task cohesion could be observed and measured already at the beginning of conscription service, which much earlier than the task cohesion. And consequently, this study is important because it identifies that these early warnings factor that predict the desired outcome, task cohesion, with up to 100 normalized importance. By concluding, we can say that yes, the task cohesion could be forecasted using this methodology. So thank you for your attention. And there is additional contacts of the authors to reach us if you are interested in our study.
Okay, excellent. Interesting paper. It's a pity we missed the opportunity to have a brief talk with the author, but anyway. We can move on to the next one, the third paper we presented today, which is a paper 102, New Approaches for Security Based on the Properties of Nano Diamonds. Jelena Tamuliene, Svajane Bekeziene, and Peter Kubicek. I guess that we don't even have the video, right, Katerina? No,
yes,
any
video is not available.
Okay, the video is not available. Okay, we can move forward. To the fourth paper, which is using system dynamics approach as a decision support tool in fighting against pandemics. The authors are Tomasz Zawadzki, Alina Zviboda, Tomasz Walecki. Okay, and the authors are here, right?
Yes, I'm here, so thank you very much for the possibility to access this conference, and please start the video.
Tomasz Zawadzki is received his master's in science and computer science from the Military University of Technology in 2005 and PhD from the Warsaw University of Technology in 2016. He is a project manager and expert for a large project on secure information for searching and sharing. This is a brief, really brief introduction. So please, Katerina, would you please share the video?
Yes, sure.
Do you agree to be recorded?
Yes, I agree.
Hello, my name is Tomasz Zawadzki, and I am representing World Studies University in Warsaw. And on behalf of other authors, Professor Halina Świeboda and Tomasz Walecki, I will present how we have used system dynamics approach as a decision support tool in fighting against pandemic. First, I would like to take a closer look of how the COVID-19 pandemic has started. The first official information about new viral pneumonia in the city of Wuhan in China has reached to WHO office at 31st of December 2019. 1 month later, the Director General of WHO declared the novel coronavirus outbreak a public health emergency of international concern. At 11 March 2012, WHO stated that COVID-19 can be characterized as a pandemic. 1 month later, number of officially noted COVID-19 cases reached 1 million, and over a month, the number increased to 4 million. Everybody asked a question how to predict evolution and spread of pandemic and what decisions should be taken. If we take a look in the past, we can reveal a well-known mathematical model of epidemic spread. It was invented in early years of 20th century by Kermack and McKendrick. The model is called SIR because it contains of three equations representing susceptible, infected, and recovered part of the population. The question is if you can add new parameters in simple way and solve more than three equations. To achieve such goal, we used system dynamics methodology, which was introduced by MIT professor J. Forrester in 50s of the 20th century. System dynamics approach assumes using of stocks and flow, which from the mathematical point of view, are ordinary differential equations. We can use as many stocks in model as is needed, and finally, we can build set of differential equations, ordinary differential equations, which could be solved by numerical procedures like simple Runge-Kutta or more sophisticated, equipped with Radau-2 scan. In our approach, we developed SIR model and added the deaf population. Here is deaf population, which is unfortunately connected with COVID-19 pandemics. We also introduced to model such parameters like population size, infectiousness of the disease, and contact rate between people. Then we tried to propose the methodology how to predict pandemic spread. First, we assumed that infectiousness of the disease is 0.2, and then we tried to estimate contact rate. Having real data until April 2012, the real data were for Austria and Germany, and real data represented susceptible population, infected population, and the general number of citizens in these countries. We tried using below formula, we tried to estimate contact rate. Having estimated contact rate values for certain period of times, yes, these are the contact rate values, we tried to estimate a function of contact rate. We used nonlinear regression for such task, and here we can see, for example, an equation which represents this estimated orange line. In the next step, we put estimated contact rate formula to the model and verified results against real data. As we can see on those figures, the simulation results were very close to the real data. For example, if we can compare simulation results, which are in black points, against real data, which are in red points, for Austria, we can compare for the total number of total cases, we can see that these results are very, very similar. It is the same, for example, to Germany, when we tried to predict infected population. And the real data, which is represented by red points, is very, very close to the simulation data, which is represented by black points. Having our methodology verified, we focused on determining if new lockdowns after holidays 2020 in Poland, would be justified. We have modified our previous model by adding hospitalization and hospitalization costs. We added to this model, we added new stock, which represent general number of hospitalizations, and having number of hospitalization, we added another stock, which represent hospitalization costs. And what were the simulation results? Simulation results show us that without restrictions, the number of infected people would increase to 15 million over 3 months. Here we have real data from the August and September, and using presented methodology, we tried to estimate number of infected people over next month. And as I said, results said that during about 3 months, the number of infected people would increase to 15 million people. And having such prediction, we were able also to predict hospitalization costs, because some of the infected should go to hospital to special treatment, and we estimated that total hospitalization cost of people who will go to hospital would achieve about 10 billion of Polish zloty. And what does it mean for the real? It means that in the short time, we could lead to collapse of the country budget. And having such predictions, we can state that introducing lockdowns were justified because of danger of collapsing budget in short time. What are the conclusions from our work? First conclusion is that proposed in early years and early 20th years of 20th century method for epidemics, I mean Cormack and McKendrick model, is still suitable for COVID-19 prediction. And second conclusion is that the system dynamic approach is valid for development and understanding the generic models such as SIR model. And moreover, system dynamics model and simulation techniques combined with nominal regression are suitable for predicting the behavior of complex environment. And what is one of the most important results from our simulation is that introduced lockdowns were justified because without them, there was a danger of collapsing the budget. And finally, we see that the presented methodology and tools should be still developed because it is very accurate to simulate such complex environments like epidemic spread. Thank you for your attention.
Thank you for your presentation. Actually, it's a kind of a hot topic, this one. Any questions? No questions from the attendee? Okay, I have one. How do you ensure that the solution will perform properly in different conditions? The mic, please switch off, switch on, level up.
Yes, I'm turned. I have microphone turned on, so now you can hear me.
Yeah.
We don't have 100% sure, but as you saw, we compared simulation results when we estimated parameters of the model in the right way, and when we compare simulated results with real data, and when we see that those results are very similar, we have some kind of sure that our approach is good. It's only a matter of estimating parameters. If you estimate parameters in the right way, we have great probability that we can predict future in the right way.
Okay, thank you. Any other questions? I guess no. Thank you again for your kind presentation. And thank you. And then we can move to the last one, which is Pandemics and Crisis. The authors are Agostino Bruzzone, Bharat Kumar Gadupuri, Wolfhard Schmidt, Paolo Di Bella, Massimo Pedemonte. And thank you, Caterina, for sharing the video once again.
Okay.
Thank you.
Hi, I'm Agostino Bruzzone from Simulation Team. I'm very glad to be here to present very quickly that is an innovative initiative about interoperable simulation. During Night Plan, there was a lot of talking about interoperable simulation, and interoperable simulation have a huge potential and application related to different concepts such as with the crisis. I will talk about pandemics and crisis. This is a joint venture between the simulation team, General University System for Future, EWOL, as well as the NATO Center of Excellence for Crisis Management and Disaster Response. We have dealing with biological contamination and other kind of issues since almost, we can say, for sure from the 50s, there was biological warfare. Now it's a little bit different because we don't deal too much to operate soldier on a battlefield that is contaminated by biological weapons, but we deal with the population, sustain the population, manage the production, and keep operating while there is a pandemics around. That's a little bit different. Obviously, military have a very good background on it. In Italy, military was taking control of the vaccination due to government decision that was speeding up the process, but it's evident that they need to work side by side with other players, and to create this kind of simulation, it's a crucial, this kind, of cooperation is crucial to train, is crucial to make analysis on procedure, etc., to identify problem interconnecting these different entity, and this should be based on simulation. We have as a simulation team different tools devoted to simulate epidemics, pandemics, Vestige, virus epidemic simulation in town. We had developed that, is HLA compliant, was tested on several cases. So it simulates the population behavior as well as countermeasure and epidemics, let me say, dynamics, logic, and how it evolves. So we simulate people by agents, is an agent-based stochastic discrete event simulation. Another one is TOPRO, that is an MS2G, so modern interoperable simulation and serious game, that was developed to educate and train people, especially within authorities, in order to be able to deal with a procedure to manage a crisis. This system can be federated and could be interesting. Now, for instance, some of our partners, like the NATO is very interested about federating this simulator with their own system in order to be able to create training session for all the different players with the benefit of their infrastructure and the classical wargaming. During a crisis, obviously, you need to consider the reaction of population. This is the reason why there is strong interest in using our intelligent agent to reproduce the population, because if you create such kind of model without population in the loop, it's not very useful. And then you need to be able to simulate, let me say, the impact of the crisis, no? For instance, you have to evaluate that if there is COVID, maybe the problem is that the town is less traffic, more clear, but at the same time, you have some much more crucial moment during the moment where people can go out, and there are impact on many different elements. School is a very good example. And there are decisions about that. One question, obviously, this is quite trivial. If it was real, it was real. The damage and the casualty that we had are comparable to a war in some way. The casualty up to July 2020 in UK was similar to that one of Battle of England along the same time period. And in Italy, we had many casualties, in fact. We learned a lot of things from that one, but we like to learn not from bad experience live, but by many virtual experience. This is the reason why we want to use strategic engineering to create models, to connect them together, to use in closed loop with data that arrive from the field, to filter and elaborate this data by data analytics and artificial intelligence, use for the model, retune the model, and support the decision. This is what we want to do. And in reality, in our case, there is a big problem because we have uncertainty on data, volatility, the situation change, the virus mutate, etc. So the validity of data is not high, but what we can do is to try to cross this information. For instance, we have even to investigate a new reaction way that should be incorporated in the model, for instance, in Topro, to be federated with some kind of maybe wargaming system where you can manage your unit on the field for the contamination, for bringing support logistics, and so on. I already say it's very different from a biological warfare. In biological warfare, there are, let me say, if it's bad, it's a really mass destruction. If it's otherwise, you need to operate over there. Now we talk about the population, and in the town there are many aspects and many impacts that we can have. I was involved in 2003 with the SARS, in 2010 with the H1N1, one in Canada, the other one in Australia. I was there with team of local and the US, Australia then, to create a model to address that. There is a big potential. By simulation, we can do a lot. We can even investigate the benefit or not of you introducing new solution, like could be UGV, to be able to deal with the drugs administration supervision in the hospital, to keep our medical doctors a little bit out of the front line. We can think about many aspects. This should be investigated, and it should be very interesting even to compare what happened in a country respect to another one. We have example in the west, east, and west of different behavior, and sometimes are based on hypothesis. We don't know exactly the situation. By the simulation, we can make guess and check if this makes sense, and so to identify what was the real source. And we have to develop the new procedure for the future that can go by supporting application on your smartphone, to decontamination, new technology, to simple procedural approach to reduce the impact and to keep the area safe and free as much as possible, considering this situation is still standing. One important aspect in the simulation model is to couple the contagion mechanism and the, let me say, in this case, virus, but in general, the disease life cycle, as well as its impact on population and the effect that you have. In our model, we simulate population person by person that interact not only as individual, but even as social network within their family, with their friend, based on the work they do, based on what is their role. So a student is an agent that is go to the school, he goes by walking, he go by bicycling, he go by the school bus, depending, maybe come back to lunch or not, if you are working outside, depending where you are. This is generated by open data and can allow us to have all this data to create a town in a realistic way. The open data are not cross-related, and artificial intelligence engine developed by simulation team cross-link that in order to create the individual. They are not exactly that one, but are consistent with our data. In the map, in the terrain, we generate even all the interest points, and then our aggregator and attractor for people from a bar, from a store, from a supermarket, from an hospital, depending on what happened. The intelligent agent manage the behavior and move the people around. And if the one is infected, is go through and infect other one with some logic based on distance, based on exposition time, based on what phase of the disease it is. This is an example where we have a crisis in a place and some initial infected people, this after a while, and then we can see how it's happening and how the crisis evolved. This is about vestige, and the top row is similar, and it is even possible to provide the user some high-level decision making that could be used interoperating with the other one. The idea is to interoperate through HLA, to federate this one with the other one, to take information about position, logistic of unit in wargaming, and information about population into Pro, investigation to simulate the procedure, and then to compare the result that we have. This is a quick overview. Obviously, we are thinking to make some experimentation. Was planned already for October. Now with COVID, we are a little bit behind the schedule, but we have already carried out intensive experimentation on that, on contamination model already with the, among this center and us, and so we are very optimistic about being able to do it. This new idea is to develop something. We are even organizing a proposal on this subject, and I feel if you are interested, we'll be very glad to keep in touch. Thank you very much. If you have any question or answer that you propose, please contact me at my email, and I will be more than happy to go back to you and try to see if we can develop something. My email, by the way, is agostino@itim.unij.it. Goodbye.
Thank you again, Caterina, I have to say. So I guess we're approaching the end of this session and the end of the whole conference. I would like to thank you all for taking part of this virtual conference. Hope to see you in person in Roma next year. I guess this would be a great conference, great opportunity to get together again after 2 years of virtual remote events. So I would like to thank you again. I would like also to recall that we have the closing ceremony just right after the sessions. So please join us to the closing ceremony. And then once again, thank you for your time, ladies and gentlemen. Hope to see you soon. Please switch on the camera so we can say hello, looking at each other.
Hello.
Bye.
Bye.
Ciao. Hello, Daniel.
Ciao.
Big achievement yesterday, right? You won the best paper. Bye. See you in Roma.
Thank you. Yeah, see you in Roma.
See you.